Hello, in this video, I am going to introduce our paper, Dynamic Slicing for Deep Neural Networks. I am Ziqi Zhang from Peking University. Program slicing is the computation of the set of program statements that may affect the values at some point of interest. In this example, the original program and the program slice on the criterion right sum is displayed. Program slicing is widely used in software engineering for various tasks such as debugging, testing, and verification. But existing slicing techniques are mainly designed for traditional programs that are constructed with functions and instructions. Recent years, deep learning networks have achieved remarkable success in many applications. This technique redefines software and starts an era called Software 2.0. We apply the concept of program slicing to the area of DNNs and define DNN slicing as computing a subset of neurons and synapses that may significantly affect the values of certain interested neurons. We demonstrate the usefulness and effectiveness of our proposed technique with three applications: adversarial input detection, model pruning, and selective model protection. A deep neural network is composed of neurons and synapses. Neurons collect signals and perform various mathematical operations. Synapses transmit signals between neurons. A program slice S consists of all statements in the program P that may affect the value of an interested variable V in a statement S. The slicing criterion C is composed of X and V. Since slicing technique was proposed in 1989, researchers have developed many kinds of slicing, such as static slicing, dynamic slicing, and so on. The motivation of slicing a DNN is threefold. The data flow analysis of slicing technique can help to understand the DNN decision logic. Slicing can reduce the size of DNN by finding the unimportant neurons and synapses. Slicing can select the important parts of the DNN and protect them with low cost. To explain our technique, we first formulate the problem. We consider one neuron N to take several numerical inputs and yield one output. A neuron M has synapses S1, S2 to Sk that are weighted with W1, W2 to Wk. Each synapse Si skews the activation value of a preceding neuron with Wi and pass the skewed value to neuron N as the input. The goal of slicing is to compute the subset NC and SC with respect to C that significantly contributes to the value of any output O for any input sample C. However, it is not easy to slice a neural network. The behavior of a single neuron is difficult to understand, and it's difficult to quantify the contribution of each neuron. Besides, how to deal with the large models that contain millions of neurons. To deal with these challenges, we propose to use data flow analysis to slice a network. Our approach, NNSlicer, consists of three stages: profiling, forward analysis, and backward analysis. In the profiling stage, NNSlicer records the activation value of each neuron for all input samples and compute the mean value. In the forward analysis stage, NNSlicer records the activation value and compute the difference between the profiled mean value and the recorded value. Finally, in the backward analysis stage, NNSlicer iteratively computes the contribution of preceding synapses and neurons. Formally, for each input Xi, NNSlicer observes an activation value Yunxin at neuron n. Then, the average neuron activation value over the whole training dataset is computed. In the forward analysis, NNSlicer quantifies the reaction of a neuron n as delta Yunxin. The backward analysis is motivated by the data flow graph in the traditional program analysis. Data flow graph defines the data dependencies between the instructions and variables. A neural network can also be seen as a data flow graph. Based on this intuition, NNSlicer recursively computes the contributions from back to front. For every interested neuron, NNSlicer only considers the neurons that are directly connected and set the neurons with non-zero contributions as the target neurons. NNSlicer supports 5 common operators that are enough to handle most existing CNN models. However, because the large size of a DNA model, updating the contributions for all neurons and synapses is time-consuming. So, we only update the neurons with large contributions, and threshold is set by a hyperparameter. The overall pipeline is shown in algorithm 1. NNSlicer analyzes each data sample respectively, and it will be very time-consuming when the dataset is large. To accelerate the slicing process, we incorporate the parallel character of GPU and multi-threading. The profiling and forward analysis are conducted on the GPU with large batch size, and the backward analysis is conducted in small batches as a separate thread. We implement NNSlicer in Python and TensorFlow, and the multi-thread computation is conducted by Ray. We evaluate the time overhead of NNSlicer. The speed for a batch of input is much faster than a single input, and the advantage demonstrates the necessity of our GPU and multi-thread acceleration. We use NNSlicer to detect adversarial samples. Our insight is that the slice can be viewed as an abstraction of the decision process, and the decision process between normal samples and adversarial samples are different. Thus, by learning from slices of normal examples, we can understand the normal decision process of the DNN. For new input, if its slice is different from the normal slice, it is very likely an adversarial input. Our approach has 3 advantages. First, NNSlicer does not require modifying or retraining the original model. Second, NNSlicer can scale up to support large state-of-the-art DNA models. Third, NNSlicer requires only the normal samples to build the defense. NNSlicer can also be used to prune and simplify networks. Existing network pruning methods focus on reducing the network size for all the output classes, but NNSlicer enables a more flexible pruning scheme on a targeted subset of output classes. Specifically, NNSlicer computes the synapse contribution to the target classes and prune the synapses of few contributions. As shown in the figure, NNSlicer can preserve higher accuracy with fine-tuning and without fine-tuning. DNA models are becoming valuable assets due to the high cost of training process, including collecting a large amount of data and expensive GPU usage. However, an attacker may steal the functionality of a model at a comparably low cost. NNSlicer can slice the model for certain classes, and it can help to find significant components for the important classes and protect them. Empirical results demonstrate the strong protection performance in front of the model steal attacks. Despite of the interesting applications of NNSlicer, there are still several limitations. Currently, we only consider CNN models, but other architectures such as recurrent neural networks and graph convolutional networks are becoming popular. Besides, NNSlicer borrows the idea of dynamic slicing, but there are many other kinds of slicing techniques, such as static slicing, condition slicing, and so on. It is interesting to apply these techniques to DNA models. Third, we mainly discuss the slicing criterion concerning output neurons, but slicing for an intermediate neuron may also be interesting. Finally, slicing a network may have other applications. For example, is it possible to slice certain attributes from a trained model, or is it possible to compose different slices to a new model? Or can NNSlicer be used to debug model or diagnose fragile weights? To conclusion, this paper proposes the idea of dynamic slicing on deep neural networks and implements a tool named NNSlicer to compute slices for convolutional neural networks. The working process of NNSlicer consists of a profiling phase, a forward analysis phase, and a backward analysis phase. The usefulness and effectiveness of NNSlicer are demonstrated with three applications on adversarial sample detection, targeted model pruning, and selective model protection. Thank you for listening.